sound out there? Can you hear me all right? Or does it need to be louder? Good, right? Yeah, okay. Man.
No, and that's definitely needed because there's so many different types of DAOs.
You just want to copy. You want to like iterate. True. Yeah.
Good point. So,
I think like
but also not
All right, there's
just constructively.
5 people.
What's up, Toby?
Yo, 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 yo.
Feeling fresh?
Definitely not feeling fresh. Feeling very run out and tired.
Aren't we all?
It's because Chad keeps making me do other stuff. Yeah.
Hush, hush. Hush, hush, Toby.
If anyone wants to do a lecture on zero knowledge, I'm ready to go. What's up?
I'm done. I have zero knowledge. Yeah.
Perfect. You're done. You've mastered it. All right, I'm going to start. Yeah, Chad, good to go? All right. Yeah, okay. So this is our last lecture for the 44 people who are watching and you all. It's really for you. But I just did, before I start, I wanted to say that I speak for myself, but I'm going to also speak for the other mentors that the work that you've done is very impressive. We're very proud of you, and I think y'all have done a really great job, especially the constraint of trying to do all this in 7 weeks. The course material from Alchemy Learn is designed to be open-ended, so we're trying to force this constraint on you to do it in 7 weeks. I think y'all have done really good work, and I'm impressed, and I just want to offer that to y'all. Everyone in here has done a really great job. So we're going to get into governance for this week, and I just thought we don't get a chance to talk about a lot of kind of culture and behavior in this space. We're really dealing with we're trying to shove a bunch of information at you, but we gloss over a lot of things that may or may not be relevant or important to actually working in the space. But does everybody know what a hardware wallet is? Yeah. Okay, do we know how to use them? Do we use them? Hopefully we do. It's going to come into play here with governance a bit. And my fancy, really expensive clicker doesn't work. For some reason it decided not to. It does this though. So I might be doing this. But it doesn't advance. So I'll be over here today pushing these. But so this is week 7, governance. The whole module for this week is basically building a governance contract. However, congratulations to you, Top Gun graduates. Impressive, best of the best right here. You should be proud. Tom is proud. All right, so here's the topics. We're gonna go over proxy contracts, libraries, contract upgradability, and governance. To get there, we're gonna do this. We will get to governance. I'm gonna start with going backwards. We're gonna go to multi-contract calls, proxy contracts, contract storage, memory, EVM, VMs, memory management, machine resources. So I'm gonna start at machine resources. I'm gonna get you to governance. Why am I doing that? Well, you can tell me if it's worthwhile or not afterward, but I thought you guys should know a little bit about how the machine is built and what you're working with. It's gonna come into importance when you are dealing with contract upgradability, because that is, a lot of people gotten burned with contract upgradability, whether or not you're using a diamond design or however you are thinking about this. There are two camps in smart contract development. One is you don't upgrade contracts. What you deploy is supposed to be immutable, so you don't change that ever. And that's the guarantee that you're putting out to the community, is this code can never change. Well, after a lot of hacks, people said maybe that's not such a great idea. Maybe we should be able to change this a little bit. Or as companies started to build up, they thought, well, this doesn't follow normal software development. We usually can upgrade. We can usually deploy patches, fixes, or even add more features. So this idea of contract upgradability started to come into the industry. And so you still have these two camps. One is smart contract is kind of like firmware. It's like once you deploy it, it is baked into the machine and you can never change it. And then there's also now we're getting into even governance where you could say, well, we could actually vote on the changes that we want to make or features that we want to add. So I'm going to start with machine resources, and I'm going to try and get you to governance. Hopefully that will make sense. If not, I'm going to take you on a magic carpet ride of computer science. Yeah. All right, so let's talk about storage. So what machine are we using?
EVM.
What is that is an initialism. What is it?
A lot of tables.
That's a good point too, right? So what's the machine that we're actually interacting with? It's the EVM, which stands for
Ethereum virtual machine.
Ethereum Virtual Machine. Great. Bonus point. Mark that. All right. What is a virtual machine? Yeah, we'll just talk it out.
It's a machine that does not exist physically, but virtually simulated in another machine that exists physically, or maybe perhaps another machine that doesn't exist physically.
Franco?
VM within a VM. VM's all the way down.
I was just gonna say it interprets the code and translates it into bytecode.
Cool. Take that. Anybody else? It's a virtual machine.
It's a
Vans?
program that can be ran on any machine. That's the same.
Anybody else? I like all those answers.
Docker
I mean,
container.
it's not what I like. Huh? Docker container? Application, kind of what Van said. Application, program. Yes? So I'm not going to read. I have a bunch of these. I'm not going to read all of them. I'll just kind of read a couple sentences and then move on. I believe our slides are available, but you can always look up what a virtual machine is. Virtual machine is a computer resource that uses software instead of a physical computer to run programs and deploy apps. One or more virtual guest machines run on a physical host machine, right? Okay, so we kind of have this idea that we have a software computer that's running on hardware, right? So you have a program that's running on metal, right? So it kind of looks like this. It's going to be really tough because I'm going to do this. It's, this thing always sounds better than it is. So you've got one machine. This is a virtual machine. This is virtual machine 2, and then the bottom, right? So this is the metal, right? And then we have these two, kind of like software programs running. Well, what we're going to do is we're going to take one of these and we're going to make this the Ethereum virtual machine. So as Sam kind of said, you could run lots of these. You could have VMs running on your machine, but also the Ethereum virtual machine could be running as well. But instead of it being its own program that you're running amongst many, we don't really do that so much anymore, but the machine in which you're deploying code to is going to be for this thing, not for this thing, and not for that thing. It's its own encapsulated machine with its own, it's got its own operating system, it's got its own storage layout and all that stuff. So we're going to get into that a little bit. Talk about memory layout. Everybody should know what this is, and if you don't, you're going to learn about it right now. What is this?
Call stack.
Adrian knows. What is it? You could say it's a call stack. I wouldn't call it a call stack. There are stack frames in there.
Is that a rest space?
Yeah, this is your memory layout on a machine. All right, tell me about it. Don't make me do all the hard work. It's you young, brilliant minds, tell me. What is it? What's the bottom?
The bottom is red from program file.
Yeah. There's no wrong answers here. There's just the right answers. Okay, so the way this works is this is a layout of the memory on your machine, not the storage. That's not the hard disk. It's the RAM, right? So typically what happens is you have the 0 address down here. You don't get to write to this space. You don't get any control over this space. And then you have the highest address up here. That's the end of your space. You'll throw in program. That's like what you'd say the bytecode or any compiled code. Anything that runs, any program that runs is going to get loaded in here. And that's what, you don't get access to that. That's just when you say open up Brave or something, right? The machine code gets loaded into here. You don't have a choice about that. You don't get any control of that, but the operating system loads it in there, any initialized variables, any other data. Then you get your heap and your stack. Okay, so these are like global variables, things like that get loaded into here. Your heap is a certain area of memory, and then the stack is the other area of memory. And typically, most machines, although I was told this is not the case, so that's fun, but most machines will have the heap on the bottom, which grows up, and the stack on the top, which grows down. Why is that?
There's no memory overlap?
Well, they will never overlap.
Well,
your machine will stop before they overlap.
Okay, so that way you don't have to move the stack up as the heap grows.
You don't have to move the stack up. Well, they're all, you could have it. I mean, what if I just said you get, I cut this in half. I'll give you the heap here and the stack here, and you can operate within the heap and the stack.
Well, I don't know. That's a good point.
Okay.
So you know your maximum size, you don't have overloads?
Well, you're already, the operating system will give you your max. You won't be able to get more than a couple megabytes in here. I
Does it
believe.
simplify like the addressing by doing it this way? But because you can just basically have a signed bit as like the negative. Or
Not so much.
something like
It's
that?
not about addressability.
Okay.
This is the best optimization layout that you can have for not overlapping. If you put them at opposite ends and they grow towards each other, you don't have to like guess how much you need. Although this, you can't, these aren't infinite resources. The operating system will usually limit these. But typically these are where your functions run. You load them up on the stack, and here's where you want like a little bit more persistent memory. And they grow together because that is the best optimized way to get the most space out of both of those. It's very difficult to optimize when they're both growing up. However, there are heaps that do go in the opposite direction. But this is your memory layout. This is where all the computer operating system like loads in resources for memory, right? Okay, hopefully that will become clear later when we talk about the EVM. So let's talk about memory addressability and word size. So you have to address your memory, right? You need to know how to get to it or access to it. And then the word size is kind of when you drill down to your machine, you kind of end up with the word size. And the word size is basically the width of the data that you're dealing with. Like how much data resolution can you store, basically. So in computing, a word is a natural unit of data used by a particular processor design. A word is a fixed size datum handled as a uint by the instruction set or the hardware of the processor. So this is the smallest piece of reference that you have in your machine to say how much information can you deal with. Everybody is like, God. So the width, so this is basically like when you talk about machines, a processor will operate on instructions. Those instructions are a certain size. There's a certain amount of bits in there that you can deal with. It could be 16 bits, it could be 32 bits. This machine right here is 64 bits. It means that's what the computer CPU, the instruction size can deal with. It means it can address memory up to 64 bits. It could, if you're doing operations, all those have to fit within 64 bits. If I'm using numbers, the integer values are going to be represented by 64 bits. Could be a 16-bit machine, right? Could be a 32-bit machine. It's basically like how much information are you able to represent? I can represent 64 bits of information. All right, if I go back here, Adrian said that there was a stack frame. Stack frame would be up here. That's where all your function calls would go. To address those spaces, the width of this is basically your word size. Like how big, how wide is that? How many bits can you shove in there?
About 64 bits.
So like on my machine, this whole frame, this is a bad analogy, but this whole frame, you'd say this was like 64 bits you could fit in there.
Big words.
Right, so 64 ones and zeros, right? Okay. You don't need to really intimately know this, but I want it in your brains. Okay, so I'm going to give you an example here. But so word size, it limits the number of addressable storage locations a machine can read and write to. Sam, you wanted memory. Well, here we go. Okay.
And I'll forget it all later.
Well, it's okay. You can. There's too much information in here to like really know. It's just you know of it, right? The whole point is you know of it. Okay, so here's an example where you have addressable memory on the far side in red, and then your memory locations are in blue. So how many, what's the word size here?
For 16 bits?
So you can just fit 16 zeros and 1 in here, right? And then the addressable memory has a whole bunch of slots that you can point to the locations in, right? So you've got 16 bits. That's your word size. That's like the width of the amount of information that you can deal with. David is gone. Okay, well, drink some coffee. Yeah.
And like a hard drive, right? Are we talking about like processors? Like this is how much memory I have within my, like on
I'll get there. Hard drive is you could have
That was like
this is
not ordinary, right?
separate.
Yeah, okay.
When you talk about memory of a system, Vans. Talking about memory of a system, you're talking about how much RAM you have, how much the CPU has access to random memory. Storage gets paged in and out. So you could have like infinite storage,
Right.
but the machine is operating within your memory layout.
So that's what you're fine.
So this is all, if you can think about this, it's all RAM we're talking about. You have CPU registers that will define your instruction set and how much information you can store in those registers is basically what gets mapped to your memory.
Right.
There's only like 8 or 16 registers in a CPU. You don't need to know any of this. I'm just giving you some background. But those are defined by, however large those registers are basically going to define what your memory layout is going to be. If you have a 32-bit CPU registers, you're probably going to have a 32-bit machine. Okay, so the word size, so this is the width of the information that we're going to be able to reference. Like the datum, the smallest data objects that we can represent are going to be 16 bits, right? Or the largest, I should say. The largest data that we can represent are 16 bits, right? And then we're going to say, well, we have 256 slots, so this is addressable over here. We have 256 of those that we can reference storage locations, right? So this equates to 512 bytes of memory. That means I have 256 slots that I can, those are addressable memory locations that I can represent the actual storage locations with. So that's 256 times 16 bits is 4096. And if you divide that by 8 bits per byte, you've got 512 bytes. So this particular machine right here, it requires 512 bytes to have this memory layout, right? So I'm going to kind of like walk us through what the memory implications are for that. So we have this kind of like little thing here. Just so you know, for this, it takes 8 bits because you have 256 slots here. It takes 8 bits of information to reference all of the memory locations, but you're limited to 256 slots. Okay, so let's do. Instead of having 256 slots, I just want to do a little bit of it's kind of like a little example here of what happens if you go one-to-one. So instead of having 256 slots that represent all of the available memory, what if you just had one slot of addressable memory point to one memory location? It's not storage, this is RAM, right? So you would have 2 to the 6, I don't want to get too far into the computer science, but does everybody know why 2 to the 16 is your total possibilities there? Namdar does, Sam does, Vans? No, okay. Does somebody want to, I can say, but does somebody want to say? Beppe?
Because it's binary, right?
What does that mean?
Binary 0 or 1.
W-
So you have two
right.
different types of data, which is 0 or 1, like off or on, and then you have 16, which is your word size. 16 bits.
So you have the option of having 0, 1, so there's 2 options, and then you have 16 of those options. So to get like the total possibilities a lot, what you'll see is you'll say, okay, so you have binary, which is 2, and then you'll have 16 slots or 16 places of those. So 2 to the 16 will give you about 65,000 possibilities. So if you have 00001, 00000, those are 2 possibilities, right? So you can get total possibilities of 65,536 locations, right? So if I have a 16-bit machine, I could have this many of those memory locations that I can point to. And if I do one-to-one, that means I have 65,000 memory addressable slots that I point to 65,000 locations, right? So if we have 16 bits per slot, we get to do this one-to-one, we'd need about 131 kilobytes of RAM to represent that. Okay, going forward. Yeah,
I was just gonna say, like,
Germano?
it's the same way with colors.
yes,
Colors, so
yeah.
it's calculated colors.
So you can address, like, so if 8-bit color, like how many colors can you represent with 8 bits? You know, or you get this, I don't know the colors, but yeah, this, what is it, the CYN?
G and
It's 256 for 8 bits.
Yeah. But then you got like, if you're doing RGB, there's like 3.
Exactly.
256 to the power of 3.
Exactly. I said there was 8-bit representation here to do 256 slots. 8-bit color, 256 different colors. This is just binary calculations for possibilities.
You see the same numbers in computer science often.
Yeah, I mean, yeah, these are physics numbers, right? So if we did 32-bit, we had a machine that could understand 32 bits of information, and we did 1-to-1, that would mean that we'd need about 17 gigabytes of RAM to do 1-to-1, right? That's like 17 gigabytes of RAM, that's not crazy, right? We see like my phone, I think has, I don't know, well that's hard storage. Like RAM today I've seen like 64 gigabytes, right? That's not uncommon. So let's go one more up. So this is 64 bits. So 64 bits of slots that point to 64 bits of different memory addresses. I would need this many gigabytes to represent that, right? So let's do the math on this machine right here. So Toby's MacBook 13-inch 2017, don't make fun of me, 2.3 gigahertz i5 has, so this machine has 16 gigabytes of RAM, right? Well, I need, if I do this 1-to-1, all the storage slots that I have point to all the memory locations. I'd need about 147 million terabytes of RAM to do that.
Is that exabytes at that point? I don't know.
Yeah, it kept going up. I was like, "Where? You guys aren't gonna know." So we've got exabyte and then petabyte. Yeah, so I was like, I'll just keep it in terabytes because that sounds really big. So how do I get 16 gigabytes that I have of RAM here to represent what I would need to do 1-to-1 that would require 147 million terabytes? Like, how do I do that? That's kind of crazy. I don't have that. Like, nobody has a machine that has that many terabytes of RAM. This is not storage, this is RAM, right? How do we get 16 gigabytes to represent all those terabytes?
iPhone 15 maybe?
Yeah, just keep ramping it up. Keep ramping it up. The other little kink here is that you want to allow every single program running on your machine to have access to all of that space. That's what your operating system does. So if I'm running 10 applications, they all get access to all of the memory on my machine. So our shadowy supercoder? Right here, they're running all these applications. Every one of these applications has access to the entirety of the memory on the machine. How do you do that? Swapping what?
Memory to RAM. Memory to disk.
Right, that's paging out, but that's not what that's what happens mechanically when you need something that's not there. But how do we manage that?
You had access for like a millisecond and then you have another one access for the
Operate?
you like threading?
Could do threading, not really, but yeah. That's like a consequence of how you manage multiple things. But the answer what we're looking for is virtual memory here, right? We're going into the virtual world. So virtual memory, I'm not going to read this whole thing, but I'll say virtual memory is a storage allocation scheme in which a full range of memory addresses can be made private to each individual running program and addressed as though they were part of the main memory of the physical computer. Just jump down to the bottom. It is a technique that is implemented using both hardware and software. It maps memory addresses used by a program called virtual addresses into physical addresses in computer memory. So this is how we get 16 gigabytes on my machine that can represent like tons of possibilities of possible memory locations, right? This is RAM, this isn't disk. So our disk is here. That could be as big as we want, but we're limited to the amount of memory. I mean, it's kind of ironic. We think of memory as like how much a computer can store, but when we talk about a machine, the memory is actually how much of RAM you basically have, because that's what the computer operates with. The registers are really, really fast on the CPU. They get you get access to the CPU to this your memory layout, and then it gets dumped to disk if you aren't using it or it gets stale or something like that. So the CPU here is basically using this page table to say, give me, I stored something in slot 2 here. What did that point to? And it points to your physical memory here. Go give me that information. If the memory here gets stale or you need more space in your page table, you'll page that out to disk. And then if you're looking for something that wasn't there, you said, well, give me, what is it, 0, 1, 2, 3, 4. Give me what I had at 4. it's not there, page it in from disk. All right, so this is how your computer works. Okay. That was as far deep as we're going to go into computer science. You just need to know that there's a scheme that operates that kind of takes finite resources, right? We have a limited number of memory in our machine. That's denoted by the width of our word size of that machine, right? And we have some kind of schemes for managing how we do that with limited resources. We don't have all the resources enabled for our machine to say, we'll go to memory address, 32 billion, and give me what's stored there, right? It says, well, I'm going to make this little space, and then we're just going to keep virtually addressing the entire memory space that we have, our operating system thinks it has, right? This is also going to come into, we touched this a little bit, I think we talked about it in one of the workshops, which is how do you represent 2 to the 56 bits of storage in a mapping, right? It doesn't all get represented, it's just what do I need to have access to? And then it's kind of like a virtual representation of I'll get it whenever I need it, but I don't need to have it represented all the time. Let's go Sam and then Germano.
You already answered by using the word virtual. I was going to ask, was that what essentially the word virtual means? Because I think a lot of people get hung up on that word. Does it mean that we don't physically have all those pointers?
Exactly.
Pointing to locations?
Exactly.
We just virtually have them?
It's like in our mind, I have access, like the CPU gives the impression to a program like, hey, you have all this space, whatever you want. And the program says, okay, well, I only need to do this little thing, and then the operating system will manage that. But it says, well, if you want to use the whole thing, you can, but I also have 20 other programs that I also say that to, and so the operating system a lot of time just lies and gives you kind of a pretty interpretation of that. You have access to all these resources, but you don't. We can do stuff like, you page in and out, or you only run one program for a couple milliseconds and another one actually less than that. Germano, did you have?
I was just going to say perhaps a good analogy would be you're creating computing debt, like a
Yeah, I guess you could do that.
credit card of
Right, yeah, you can use this for now, but you don't necessarily have to pay for it right now, right? Okay, so what does this have to do with anything? Well, let's go back to the EVM, okay? So what type of machine are we programming for? It's the Ethereum virtual machine. So what are those specs? Yeah, you don't know. Nobody does. This does. Does anybody know has anybody ever read this?
I actually skimmed through it.
Yeah? Okay, well, we know it exists.
Why is it yellow?
Because the Bitcoin white paper was white.
But why yellow though? It shows it.
I don't know why I only know that it was not
Just for the record,
an
they
alter.
actually had a white paper, and then they came out with I think it was a second yellow paper as a preface for the more features that they were planning to add. I think the yellow paper is forever changing, but the white paper was the initialization of what they were trying to implement.
I think didn't Vitalik initially write the white paper? I don't know.
He did.
And then I think this is the technical spec. The yellow paper is the yeah. If you ever hear Gavin Wood speak, I would recommend it. Very smart guy. Who built Ethereum? It's interesting. Okay, so I'm just going to read the top here. This is from the Ethereum white paper. I would just know that it exists if you ever need to dig down in there. But I think I've probably 5 times referenced this, so it's not something you're going to do every day. But so 9.1 basics. The EVM is a simple stack-based architecture. The word size. You know what word size is? Yeah. The word size. Well, you don't even have to know what it is, but you know that we referenced it here. It's 256 bits. Why? This was chosen to facilitate the KEKAK 256 hash scheme and elliptic curve computations, right? So it's natively going to accept what the hash spits out, right? And the memory model is a simple word addressable byte array. The stack has a maximum of 1,024 stack frames, right? That's going to be important. Okay, so our word size is 256 bits. Our memory addressability is word addressable. And we have this stack versus storage contract thing. Yeah, 256, really big. Okay, so here's our memory layout. We have storage. This is like contract storage. Starts at 0, goes to 2 to the 256 minus 1. It's 256 bits wide. Hopefully I laid this out so it was familiar with the one before, right? So you start here and you go up, or you increase in I don't know, increase in the increasing numbers. Size, I mean, what do you say? Like, you're just increasing the number, right? So the memory is a word addressable byte array. I just made it horizontal because you can think of it as vertical. It's kind of the idea or the analogy that they give of it, thinking about like a computer science array, which would be just an indexed array. You can read 256 bits wide. Question? No? Yes, no, no. Okay, and you can write in either 8 bits or 256 bits, and it scales quadratically, so it gets kind of expensive to write to if you do writing a lot. And then you have your stack, so this is your call stack, and this is 256 wide, so the instructions that it can take are 256 wide, which means like put on the stack this really large number that's 256 bits. It can take that. But it's only 1024 tall, if you want to say. So what does that mean? Well, it means this is where you revert when you revert. All right, you revert right there. If you put up a lot of opcodes, and a lot of those you don't have access to actually because the machine is doing things for you. If you fill it up, you will revert. And you will see this. I've run into this a lot when if you're doing a really complicated function and you're putting a lot of variables in that function, a lot of local variables. At a certain point, the compiler will tell you you need to use less variables because your call stack is full.
Stack too deep.
Stack too deep. There we go.
Is this like stack frame? Is each function in Solidity a stack frame, or could there be multiple stack frames in a single function?
So you're going to think of this. Each one of these is an opcode.
No, opcode. It's not stack frame. Okay.
It is a stack frame, but the opcodes get shoved in there. So store, read, jump are all put in here. And each one of those opcodes has gas associated with it, right? This is how we calculate this stuff. All right, so our word size is 256 bits. Here is the implementation of Geth, the Golang implementation of the Ethereum virtual machine. That's the op imstore, imstore8, sload, and store. So what this takes is a pointer, which is a uint 64-bit pointer to the program counter. The program counter is basically the amount of resources that you can use to operate all of the addressable space, right? So this isn't truncate the 256-bit word size that you get to deal with. What it says is within operating a program on the Ethereum virtual machine, I can have like instructions that are 64 bits, a 64-bit number, which is really, really big number. You're not going to even use this much resources. So not only do you have a really large word size, but you also have a lot of space to account for what is happening in the program. And because you're so resource constrained with gas, you will never use, like that's just a huge amount of program counter resource. And the program counter is basically just going to keep track of like where you are in your instructions. Like how many instructions do you need, where are you jumping to, all those types of things. You don't need to know exactly what it is, you just need to know that you've got tons of resources on this machine. You'll never ever use fully. Okay. So let's go back to storage. So the contract storage starts at 0 and goes up, right? So why do we care about that? Well, the proxy, that's going to come into play when we deal with proxies, because proxy contracts are going to deal with the contract storage in which you give to it. So what is a proxy contract? What is a proxy? Do we know what a proxy is? Yeah.
Proxy basically stands in for something else. Is a generic description of or abstract.
Stand in? Anybody else? Yeah?
Yeah, like,
No.
maybe perhaps like a more digestible amount of data for a bigger thing.
Like a representation type deal? Epic.
Similar to how like a VPN works, it's like a middleman almost.
Middleman, intermediary. Okay. Webster's dictionary says a proxy is an authority or power to act for another. So if I just ram in a contract into that, I say the authority or power of a contract to act for another. Okay, so that's the idea of a proxy contract. You can have an intermediary representative that will have power to act on the behalf of another contract. Kind of works like this. What is it? Shadowy supercoder? It's over here. That's an EOA. It is not me. I would be much more rich. All right, so that's your EOA. What's our EOA? What does that stand for? Look at this. Peanut gallery. All right. Nice. Okay. So our externally owned account will interact with a proxy, and that proxy will point to an implementation contract, right? So maybe the logic is here, but we interact with this contract, right? And then I think Adrian, well, Adrian's referenced something later. So what I can do is I can still interact with the same contract, but I can use a different implementation. So the idea here is that this address doesn't change. I can always just provide that to the community and say, hey, everybody, USDC or Tether or CryptoKitties, here's the address, right? And from that, I can have different implementations if I wanted to, because this contract will act on behalf of what is actually executed here.
If proxy is a smart contract, and it's, how do you get proxy to, I guess you could just make it a variable?
Yeah, does everybody, do I assume that everybody with the folded corner knows that that's a smart contract? I assume that, but is that clear?
Yeah,
I should change that.
Yeah.
Should change it. Wait, if it just had
But
just
his
4.
question was about if it's a smart contract, how do you update the smart contract if it's already?
I know, but what I'm concerned about is if everybody understands of this thing, because I put these in everything, and if you don't know it. So we'll get to that. So that deals with upgradability, right? How do I upgrade this if I'm dealing with this thing? Is that what you're asking?
Yeah, I mean, it will be a Sam answer, but yeah.
Would Uniswap be an example of a proxy contract?
Is it? Should we look? We'll look later.
Okay.
I know the answer is yes. I know for a fact like USDC is because I told you last week, like I was looking at that, and there's a lot of like fallback, just forwarding calls to other things. Okay, so let's talk about libraries because that's in this week as well. Actually, this week is all governance. You don't even do any libraries, but we hit them all the time. Has anybody ever heard of SafeMath? This library is synonymous. Like everybody uses it. Why do we use it? You don't need this anymore, actually, which is kind of a nice little treat. You guys are lucky.
Is that related to Common Core? Or?
No, this is just basically a library for math. And it back in the day, before the compiler handled overflows for you, this would account for if you overflowed your adding or subtracting, it would throw an error. So that is used all over the place. Now people kind of make their own math libraries, but you have signed math. What's signed math? If this was, I'd say, unsigned. Signed would mean that you could have negative numbers in there, like a signed integer. Yeah, I know, that's bad naming. But there's 2 styles of these libraries. I think Adrian did reference this last time with what can be in a library. But before we get there, you can have a library that gets pulled into your contract, right? You take all that code, it's like almost inherited. It's not inherited because it's not a separate contract, but it gets pulled in as if it was inherited. You could have that in your code, or it could be an external call. It's deployed somewhere, and then you interact with that contract, right? So strings, if you guys are doing NFTs, I know these are that you use a string library a lot. If I import strings, and I'm using strings for uint 256, tell me how that makes sense, then it will pull this, if I import it, it will pull this contract code into this contract itself. If I like verified it, you would see that it's one of many contracts if it's a flat file. And you would internally make calls to this library, right? But I can also have the library deployed. And if it's deployed, I can make what's called a delegate call to it. A delegate call will grab whatever's in that deployed contract and run it on top of my contract, right? So I run your code on my state, right?
If you're doing a delegate call and then that library math, safe math also changes because it's also using
The proxy.
another proxy, like how does that affect your security?
So you're saying if this uses this and this uses this
Yeah,
and this
that
changes, well, what do you think would happen?
Your yours would fall apart?
Not fall apart, it would just use this this logic over here. If this changed, it would use.
If that logic had changed in a way that you weren't expecting it to change, then wouldn't that traverse?
Well, so this happened. Does anybody know what, Chad, can you help me out here? The multi-sig wallet for,
Parity?
what is it?
Parity?
Yeah,
Are you talking about parity now?
the parity, they were using a math library and somebody destroyed that library and then it locked their, or was it? No, it was a multi-sig. I think it was a multi-sig. It was a deployed multi-sig that they were using and somebody just destroyed it. They ran self-destruct on it just because they were playing around. And it like locked a lot of funds for them. So yeah. So what I would say, the answer to that is I would personally, if I'm using a deployed library, which this is a way to save gas, right? Because you don't need to import that code, so it makes your file smaller.
Deployment gas or?
Deployment gas.
Oh,
If you're actually running the calculation, you'd have to look at how much it costs to do the delegate call.
It's a trade-off then.
Yeah, it is all. Well, every part of this is a trade-off.
So is that just like the reason of like using an external call versus just importing versus like inheriting?
Yeah, that's what I was thinking.
Yeah.
No, there's more reasons than that, but that does fall under here. I would say if I was using an external library, I would make sure it's immutable. Like it is not itself a proxy. I would say, what is in that code?
Yeah.
Do I does it work? And then you would kind of audit that. And if it works and it works for what you need, then you could use that. But I will say, like, if you needed access to a lot of libraries, you're not going to be able to deploy all those.
Right.
So if I needed access to like a calculus library or an integer math, if I needed access to strings, if I needed access to a bunch of stuff, I can't fit all that in my code because there's like a 24 kilobyte limit on the deployment. I mean, that changes with some L2s, but typically you have some kind of limit on how much code you can deploy. So there's a factor in there, but typically, I wouldn't necessarily use another proxy. I would say, like, what code is running? Because that code runs basically in here on your state, right? But the delegate call is kind of this kind of like neat little thing. It makes it possible to implement the library feature in Solidity, and it's reusable library code that can be applied to a contract storage. So this idea of delegate call opens up upgradability and governance for us. And is everybody clear on what that is? Because that's kind of an important one. I want you all to get that. So you have a call, right? Dot call. We can use that to transfer funds and things like that. I think you've used that. This is a dot delegate call. It's right here. Does everybody know what this does? It uses this code and it changes this state. Okay? Is everybody clear on that? It's kind of a weird concept. Yeah.
Is it, instead of calling into another contract and by doing a regular call, that contract is running and is running using the state within that contract's deployment? Whereas a delegate call is saying, take that function and apply it to my contract.
Exactly.
It's almost like inheriting at runtime, in a way.
Yeah. It does. It operates.
Runtime.
I don't know if you could think of it that way. I don't know if that's what happens,
Yeah,
but it does pull like this code onto the stack. It just uses your state. So, like you said, if this was a call, the call would do stuff over here and then return whatever you wanted to return, right? It would change things over here and say, did that happen or not? Like this would happen with a token. This is what happens when you transfer balance, like a transfer token value, right? You say, change like some kind of state on this contract and then tell me something back. True or like, did it go through or not?
And not to throw out like the science, CS science, computer sciencey terms out there, but would this technically be composition over inheritance in a way? Because you're kind of like composing your contract with other functions.
Typically, composability means you can interact with. Maybe.
Yeah.
I don't quite know if it
The different model. I was wondering. about
fills
that.
in. Maybe.
Maybe.
We'll say maybe. All right. So now that we have a delegate call, Devin, do you understand what the delegate call? You can say we can talk about it later if you a little bit.
Bits and pieces, yeah.
So I'll go through one more example with upgradability, and if it doesn't, let me know. And then if it really doesn't, we can talk about that after. So with a delegate call, we can do upgrading. So what does that look like? So we have the power or the authority of a contract to act for another contract, right? So this one gets the request. This one does the request, right? So if I have some state on the proxy contract, so I have X here, right? And I have this function over here. You know, you see that the state is mirrored, right? And then I write the logic here. So I have this function f of x, and it says that x is equal to x plus 1, basically, right? All right, so if I call f of x on this contract, it writes 1 into the state of that contract. Also writes 1 here, but we don't really care. This is the contract we care about. This is where our state is. By state, does everybody know what I mean by state? It's the storage, it's like the physical... Yeah, everything. It's your total, like, snapshot of all of the memory within your contract. All right, so I forwarded a delegate call. I said, hey, run f of x. F of x runs, and then it changes my state here. Is everybody clear on that?
So Toby, real quick, all your state has to be defined in the proxy contract prior, correct?
We're going to get to that. The answer is yes. Otherwise, this is Namdar's question, which is how do you upgrade this contract if you're pointing at these, right? Okay, so what if I change the implementation from here to here? And I say we have state, we have x, y, and then we have these two functions here, right? So we have f of x is x equals x plus 1, and f of y says that y equals x times 2, right? So I call f of y, what happens over here? Yeah, that state updates, right? So we had, what is this, f of y, it says, so before I had, this is 1, right? So it says, all right, whatever's here, so this is x, whatever's here, multiply that by 2 and save it here. And that's what happens over here. It says, well, what's here is 1, multiply that by 2, that's 2, store it there, right? So we get 1, 2, right?
Well, what about the other?
What about the other what?
What about that new implementation you're pointing to? If it doesn't have the X state that the old purple implementation had, and since we switched to this new implementation and maybe it's just freshly deployed, does it have any state at X?
That's a good point. Okay, so this is 1 here, right?
We don't care about it, but it's there.
Well, and then I don't care about it here either, because it's 0 right there.
So
X is 0.
what if there's like some math that doesn't check out on the red's implementation state? Like division by 0 is probably going to fail or throw. I don't know.
So that's the execution. So if the execution reverts, it's going to revert.
But does the execution's happening on both contracts, or is it happening in one? What's going on?
Happens, well, it happens on your stack.
Okay, so it's only happening on the proxy.
Well, the state is changing here.
Yeah.
Only the state is changing there. So you're saying, like, if I do x plus 1, I don't care where it told me to do x plus 1. I'm just, x plus 1 goes on the stack, right? Plus, you get an opcode for addition, right? I don't care where that logic came from, but what I do care about is where does it get written to and where does it get read from.
But is it actually mutating state in
No.
the implementation?
Yes, yeah, it does, but we don't care because I never read that.
But what if it fails to mutate on that contract state, but doesn't fail? It's valid on the proxy, but invalid on the implementation. Does that cause an issue with your proxy contract?
It could. This is why you get to initializers,
So you want to initialize with the same state?
typically.
Things like that? Okay.
It could, if you do get off, I see what you're saying. Like if there's some kind of state that would fail here, but wouldn't necessarily fail here because this one carried over,
Yeah.
it would fail.
Yeah.
So there is this concept of initializers, which we'll get to. I won't get to it in this, but you do get that in the modules of this idea of initializers. Although if you're in the week 7 Discord, I show you why initializers don't work either. So it's kind of fun. Question,
I
yeah?
was just gonna say, so you're basically leveraging the computing to a different contract, right? To
Leveraging
save on
is a loaded word. We're giving ourselves the ability to change that. We're giving ourselves the ability to change this stuff in here.
The function.
So I could say f of x here could be plus equals, that might be confusing, I'm sorry, I should have been more explicit, but x could be plus equals 2 in here. I could do that. Here I just added a completely different function.
Yeah.
And it's a bad example because I also added state here, which we'll get to in a minute because
But
that's a
is it
check.
like the main purpose of the proxy to save on gas?
No, main
Okay.
purpose of the proxy is this address never changes. And I can change these.
Oh,
And the
okay.
state doesn't ideally ever.
Hopefully. What's that, Greg?
It's for upgradability, right?
It's
That's
what?
the main purpose?
It's what?
The proxy is for upgradability?
Well, there's different reasons for proxies, but you could have a proxy that is upgradable, and this is how you would do the upgrading, right? You would point to different things, and then you would, and those things could change, but your proxy is, and you'll see there's a couple different versions of proxy contracts in the modules. You could have just a pass-through proxy, which has a fallback function and just forwards everything through it. Or you could, but that is harder. What happens with that is, if you're trying to maintain state, you would wipe out your state every time. So then you get this idea of upgradable proxy contracts where your state is stored here, execution runs somewhere else, but you always maintain your state. And that address never changes, right? You're always pointing your users to the same address. You don't lose state over upgrades. That's the kind of idea with upgradable proxies. Yeah.
Just like a quick one. So like the main reason why we use other contracts to point, like a proxy contract to point to another, is because functions themselves can't change, but the state can. And so
Well, ask yourself that question. Why don't I just keep changing this?
because we can't.
Yeah. Well, you can, but it will make a different contract address. And then you'll say like, oh, users, last week we were at 01234, now we're at 0456. You got to change. And then the next week after that, you say, oh, we're changing again. And then you lose your state, right? And then you lose your state.
So that means that you can have like an owner that can pass in like a contract address or something to kind of then call through as like a variable that changes. Okay, that makes a lot of sense.
Okay.
That makes a lot of
All
sense.
right. I'm just going to get to why this is dangerous. Okay, so we got there. Chad, let me know if I didn't answer that question. I kind of forgot it. But I'm getting to this idea of proxy upgradability. Okay, so the code is used from the implementation contract. The state is changed on the proxy contract. Proxy contract address stays the same. Implementation contract can be changed with different code. Right, not addressing Sam's point, we don't address that here, but it could be the case that your state in your proxy could be different if you re-implemented a different contract. Your state could be different if you don't handle that. But for this one, let's say that our proxy contract is 1234, right? So the user always sends transactions to 1234, and in our proxy contract, this points to 3333, right? We have 111, 222, 333, right? Okay, so storage layout must persist across upgrades, right? We don't care what this storage necessarily is, but the layout needs to be the same. Why? Yeah.
Is it because the functions act on that layout? So if you were to have a different layout, the functions would be essentially acting on unexpected data structures.
Right, it's expecting the layout to be, well, it doesn't really care, but if the layout changes, it will change how the data is read and stored, right? And we'll see that here. Yeah.
So when you say layout, do you mean like X is uint 8 on the implementation? X also has to be uint 8, right? Otherwise it would.
Right, so if you go back to this way, the bit, the word size, you get this length that you can shove things in, right? You get like this box.
Right, so if you're trying to shove in something.
So if I have an 8-bit representation, I either get that in one 256-bit storage slot, or if there's a couple of those 8-bit integers, I can stack them in there. So if one of those changes, it will affect how your layout is changed, right? So you have the data type, which is important, right? And as we'll see, you also have the actual variables themselves. Yeah.
Does this go back to something you said a few weeks ago about how sometimes it's not always an inefficient thing just to choose 8 bits because you have such a large word size anyway?
I see.
And so, if you're only using one 8-bit integer in your state for your whole program, you're still getting allocated 256 bits onto the machine.
Yeah, so the compiler, strangely enough, optimizes 256-bit integers. So you will save on gas if you use those. However, if you're dealing with structured data, you can be very crafty about how you lay that out so that you can actually fit your storage footprint. You can make it a lot smaller by putting, let's say, like 3 uint8s together instead of saying, well, yeah, I have a uint8, then I have an address, then another uint8, and then I'll have a mapping. So you can put those together in a way in which the actual footprint becomes very concise.
Is there economic savings to optimizing for storage footprint? Because it
So every opcode has a gas cost.
Okay.
So if it's having to do more, I think this is more of how much it costs you to write and read.
I see.
Because those are the most expensive process. Actually, the contract deployment is the most expensive opcode. Then you have a then you have a write is the next most expensive, and then you have a read. Those are the most expensive things to do on the EVM. Yeah. So this would be how to make your layout more concise. Where would the savings come in? I guess maybe it would be
You're writing less.
I think it's deployment gas in that particular one, but I don't know about computation as far as like you had said you wanted to see like pointer arithmetic. I don't know if it's more optimized if it doesn't have to go to if it doesn't have to jump to an entirely different like memory address. If it can point to the same one and then go in, I don't know.
Oh, okay. Interesting.
Okay, let's see what happens with. Don't do this. Okay, what were we not doing here? Okay, so. I see. Okay. So there's a subtle change here, right? I have X here and Y here, right? X, Y. What happens if I switch them? The implementation switched. Same data type, uint whatever, uint8, but the first one is Y and the second one is X. So what happens when I call, don't do that. What happens when I call f of Y on this?
It'll be looking for that place of memory where X was previously, no?
Well, let's just say, so if I call, okay, so what's my state? X is 1, Y is 2. I call f of Y. What does Y do? It says take whatever is in X, which is here, multiply that by 2. Well, what's here? That's 2. It's 2. So I say 2 times 2 is 4, save it to Y. Y is here, so it writes it there. So it puts 4 there. Right, did I do this right? Man, I was like, really, this is so confusing. Right, so I called f of Y on this contract, and it wrote 4 on my X. All right, I didn't expect that to happen. So what happens when I call f of X? F of X says take whatever's in X, which is here, right? What's here is now it's 4, right? That's my state there. Add 1 to it, which is 5, and store it in this spot, right? Which is my Y. So now I get 4, 3.
Is this a feature or a bug?
Good question. Well, let's see. You tell me. Here we go. Here's my state. Proxy contract says your implementation is an address. That's my first storage slot. Next storage slot is X. Next storage slot is Y. I point to 3333. Implementation contract. First is Y. Next is X. All right. No problem. Here's back to our storage layout. We start here. This is where when you have contract storage, you start here and you go up, right? Okay. So I have this storage. So slot 0 that's my implementation address. Slot 1 is 1, that's X, and this would be Y. And then the implementation would say I have Y here and X here. Okay. So I run f of Y. What happens? F of Y, what does it do? It takes whatever's in X, which is here. That's storage slot 1 technically, but yeah, let's take 0, 1. Let's take this, okay, and then add 1 to that, so that's 2, and then you write that to storage slot 0. Okay. So I wrote 2 here. This is what storage slot 0 is. When I call this proxy, it points to 0, 2. Okay, everybody should be like, "Oh my God, what happened? You lost your implementation. You just bricked your contract."
Can you go over that?
Yeah, we can go over that many, many times. Yeah.
So this seems like a malicious attack vector for upgradability, where you could present an implementation that appears to be correct, and kind of get out from underneath auditors in a way if they're not paying attention to the ordering of the declaration of the state.
this is malicious, this is by accident, this stuff happens all the time, and
so
they're...
my question is, what safeguards do we have for tooling to kind of catch these things if it's accidental, or catch these things if it's malicious?
Right, so that's what the module is about. It'll show you, what the idea of initializers are, what some tools are you can use to protect against this, what the current design pattern is. There's an EIP for this. It's kind of fancy. DApp idea, great. Okay, let's go through this one more time because it is very tricky. First of all, what did I do here? What did I mess up first?
The order.
I switched these, which is awkward, right? I switched those, which was bad. That was a carryover from the previous one. But what is the really, really bad thing?
Is that the names?
How many of these do I have?
You have two.
How many of them are over here?
Three.
I inadvertently kept what I thought was important, which was I need to represent X and I need to represent Y. But I also really, really, really want to implement or keep track of what my proxy contracts points to. That's an address, right? What happens is I left that out here. So think of this as, you have this block of memory. It sits in here, and you have this block of memory that sits in here. This one operates on this as well, but it changes it over here, and we only ever read our state from this contract. So what this does is it say, when I call f of y, I'm looking at this, right? This is here. I'm looking at it. And I'm calling the code over here. But the way that I've told this code that it has access to variables is that you have a variable in slot 0, a variable in slot 1, and then that's it. Over here, I have an address in slot 1, a variable in slot 2, 0, 1, and then 2. Here I have 0 and 1. First of all, I have a mismatch in my layout. Second of all, I've done a really bad thing where I said the most important thing is what the contract points to. However, I left that off here. So what this does is say call f of y. So f of y says, all right, I'm going to store something in y. In here, that's the 0 slot, right? Take whatever is in x and multiply it by 2. Well, x is my slot 1, so I'll look at that and I'll say, all right, because I'm looking at this data here. It says I have 1 there, right? So this contract doesn't look at this contract. This contract pulls this in. It doesn't pull it in literally, but it uses this for on the stack, runs the numbers off of what the storage layout is here, right? So it says, great.
It doesn't pull in the state, it pulls in the function, right? It implies the function.
It uses, yeah, that is what runs on the stack.
Yeah.
It doesn't like pull it in there and then do any, the basically you just told the virtual machine, go to this address, pull the execution code, and use the state that is in this address here, right? So what it does though is it says, okay, whatever is in X, which is my slot this, multiply that by 2, so 1 times 2 is 2, and then store that in whatever's in slot 0. It gets stored here, right? What happens is I just overwrote what this is pointing to.
With just a variable, like with what y?
With 2, yeah, with 2. Because it doesn't care, it's using this layout, but you've confused it to say, I messed some stuff up here. What happens is, when you tell your users to interact with this contract again, it points to whatever 2 is, right? Whatever that is. We don't even know what that is. We don't have control over it. We don't have anything. And if it does nothing, we just bricked it. Like, you can't use that contract anymore because what happens is it says, go ahead, call y of, x of f of x. It goes, okay, well, let me go to 2. 2 doesn't even exist or it certainly doesn't have f of x on it.
But I thought implementation was a state though, so can't I just rechange the state?
Of
Like
which?
back to
So it's not permanently bricked, you can fix it.
Hopefully.
Do I? Do I?
You have to build that in beforehand.
Yeah.
Yeah. But that's the whole point of the proxy, right? It's already build that in.
So everything, yeah. So the answer to the question Chad had, and I think Namdar had this earlier, was all the state has to be laid out initially. Laid out, like you have to know everything that the state can do. And if you need to change the state, then you have to redeploy this, and then you have to tell everybody, all right, well, we're looking at a new contract here.
Interesting.
Yeah.
So there's limitations as to what type of changes you can make to, or like what sort of, your ruggability is limited.
So I put into the Discord this auditor Riptide who got 400 ETH for finding a bug with Arbitrum's sequencer. And they used an initializer, which, you know how we write the constructor in all of our smart contracts and that runs once on deployment? Well, what doesn't run when you switch and deploy a new implementation contract? Your constructor in the proxy. So the way you get around that is you write initialization functions that will run every time there's like a new upgrade. And that should kind of like manage state and also do things like, well, set things that need to be set on this. Like if this points somewhere else, make sure that that's pointing at the right spot. Well, Arbitrum had a little mistake in their initializer, it didn't run. So it had one of these things where it was like, well, whoever wants to be able to upgrade this can upgrade this. And it was like address 0 and anybody can like shove in their own address. So you could basically like make this I think it wasn't their bridge, it was their sequencer, but it controlled like what all the money was doing. And so you could basically tell that where to point. And it was a huge bug.
So it's either pay up 400 ETH or I'll just take it myself.
Right, it was like, it's funny if you watch, follow this guy, because he has like, he shames companies when they like don't pay for audits and stuff. It's like, they go on a wall of shame, so it's kind of funny. But that one I thought was particularly interesting because Arbitrum has a very, very good team, and they still messed it up.
Yeah.
You know, everybody messes it. We all mess it up. That's kind of the idea of contract upgradability. For governance, we put all of that together, and we kind of let the community vote on implementations, when we switch them, things like that. So we kind of say, let's vote on when to make change to an upgradable contract. And so this stuff really has the power when it's all on chain. If you want to like vote to all wear purple shirts one day, that's less interesting than when you say, we're going to release funds from the treasury, right? So you can do that on chain. Can't really make people wear purple shirts. Maybe you can, but I don't know how you do it. So this is kind of what the layout is, right? So we have, everybody has some voting tokens, and somebody makes a new proposal to target a new implementation, and they send that to the governance contract. So our top shadowy supercoder says, hey, I want to make a new proposal. And so that's proposition 1. And then everybody gets to vote on that. So there's a new proposition that came up, and everybody can vote. And it makes quorum, which means, you know, passing vote, however you want to calculate that. After the voting period, you can send a transaction and you will switch the implementation, right? And that's all on chain. And that's all done by voting. Like there's no intermediaries there. Well, everybody basically comes together. It's a decentralized way to switch, to make that switch. And there are different ways to do this. I mean, you don't necessarily have to typically you have to wait on the voting period in order to do something, but you could also have it automatically engage if the quorum is hit, and that's how your governance contract will work when you do it. Let's see now, yeah, okay, I'll kind of run through one gotcha that I found with the hard hat task for governance, but before that, I just wanted to show you like how this actually works, because one of these companies that I followed for a long time actually does this a lot. I mean, there's lots of companies that do this, but Hop is one that is, they're a bridge. Basically, you can use Hop to send funds to L2s. And they have a pretty lively governance community. So this is just from their page about how to do their governance. So this is the process. So they have the forum that people can use. They use Snapshot, which is a very common tool to see. You can either do temperature checks, or that's how you can allocate voting distribution by a certain snapshot, a certain time period to see who has what of the coins. And then they use their governance portal. They have one, and then they also have Tally XYZ down there, which is a DAO platform for voting. So it kind of looks like this. You can do a request for comment, ask general, you start this way, should hop governance add liquidity, right? So these are all on-chain things, right? What can we do on-chain? And typically, if the community supports it, you can actually, make a proposal and then vote on it, and if it passes, you can enact it, right? So they do a temperature check, either through their forum, also with Snapshot, and asking for comments, and they go through a whole process. Let's see, after the end of 5 days, whichever option has the majority of votes wins and can be included in a governance proposal for stage 3. A 300,000 hop yes vote quorum is required for a temperature check to pass, right? So they do this. This is what they do all the time.
This has actually been updated, and 1 and 2 have been kind of meshed together so that the timing is like faster.
Say again? Oh, you're saying this has been updated? Yeah, awesome. Cool. So they have, here's the actual governance portal where you actually make the vote. And the idea here that I want to stress is, one, this is happening in the community. Like, this is a project that does this daily. You'll see they do it the exact same way in which the governance contract that you'll work on does it. And it's all on chain, which is kind of exciting, but also, again, you can't make everybody in Hop's community wear purple shirts, but you can maybe allocate where their treasury is going, right? Here's how here's how you make a formal vote. I'm just, this isn't, you don't need to know all this. I just want you to know that they've all laid all this out and they're doing it. And this is exactly what the contract that you're going to write, right? And here's the glossary, right? You have ERC20 tokens. You have the delegation of those tokens, right? You can make proposals. There's a quorum, which needs to be satisfied in order for the the proposal to pass. You have the voting, which actually is happening. You're making transactions on the governance contract. There's a voting period and there's a time lock, right? I thought this was interesting. A proposal is code that is executed by the governance contract through time lock. It can replace the governance contract, transfer tokens from community treasury, or perform an almost infinite range of other on-chain actions. So it's on-chain, right? So I just want to point this out because this stuck me, and I don't want it to. It's kind of a pain in the ass to get around this. But here's the contract that you'll basically build for the entire modules. You'll build the governance contract in Solidity, but for the task that you have to do for this week, you just have to engage this governance contract. So you'll make one, my governor. What does this mean? Brilliant, we've done something right. governor settings, governor, blah, 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 right? And so what is this?
That's you're invoking the super
Oh, yes.
of the contract. Your base contract of what you're inheriting, you're invoking its constructor.
Constructor keyword. So the constructor for governor has some kind of input that's probably the name, because that looks like a string. This one, the settings, has 1, 2, 3 settings. Governor votes has the token in which you're going to be using. Here, it's an ERC20 token that I think you like basically add to the supply of it. So that's an address. This is the percentage of votes you need in order to pass, and then there's a time lock here, right? So be careful with the block. This is the number of blocks you need in order to activate the vote, and this is the amount of time that voting period is active. So don't do like me and put 5 here, because that's 5 blocks long in which the voting is active. And so you'll never be able to pass. Well, you will, but then you have to write a really complicated script in order to make the voting pass in 5 blocks, because what happens is they say to reference the Open Zeppelin governance wizard, which are kind of fun. Didn't we show wizards once? Yeah, I think we did. Yeah, they're kind of really nice. So you have the voting delay. That means you engage the vote, right? Then you have the voting period. This is 1 week. All right, 50,400 what? All right, how do we get that number? 12 divided by, no, 12 times. Or you could do, so 60 seconds divided by 12 gives you what? I've already done this, I'm not that smart. 5 blocks per minute. How many are in a day? Well, there's 60 minutes in an hour times 24 hours in a day times 5, what is it? Or times 1 hour?
You can find the number of seconds in a week and then divide by 12.
Don't we have computers for this?
Well, I mean, no, I do this stuff, I always calculate these. Anyway, there's 50,400 blocks in a week at 12-second intervals, right? So don't make this really small because you have to do these, you have to make the proposal, then you have to wait a block, then you have to vote, and then you have to engage, and then you have to like execute the vote, right? Well, at 12 seconds, blocks go by in like a minute. So if you don't do all that in a minute, your proposal won't pass.
In hard hat, if I was to test this, is there a way to speed up?
You can change the time, yeah.
Yeah.
And that, if you see it, if you do a generic hard hat, there's a lock contract is the first one, and you can see how they put in time. They use time with that. And Foundry will do it as well, where you can change the time. Right. And then it'll show you, it'll say like they'll do a unit test in hard hat, and they'll show you like, okay, well, when you do this, you should change these values because we were doing this for unit testing, right?
Okay.
All right, so then you got the proposal threshold is here. That's just like how many, what is the proposal threshold is how many votes you need in order to make a new proposal. You're gonna make it 0 because you're just testing it out. And then the quorum % is 4. You can leave those as default. This is just the 1 here. You want this to be 1 because you don't want to wait around, and then because you're going to deploy this to Goerli, so it's going to be on a testnet, so you don't really have control over that. And then you just make sure that's something that's 1, you have to wait for it to be over in order to execute the proposal. So you don't want to make it a week because in order to do the task, you'd have to wait a week. You don't want to do that. But you also don't want it to blow by really fast. All right, so we've talked about all of these things. And the final project, again, just to reiterate, is a full stack application, right, with a smart contract and a front end. Some of the stuff that you're responsible for is the project name, GitHub repo. It has to be live, so it's going to be deployed. And Cloud will be heading up a workshop on how to deploy a front end, a whole dApp, pretty easy, because that's one of the requirements. If you don't know how to do that or just want to see how he does it, I would encourage that. Description, short, long, how did you make it work? Presentations, right? Logo, cover image, screenshots, and the demo video. So, and we're accepting hackathon projects from ETH Denver as well. So if you do something there, you can turn that in to us as your final project. And then if you want, I can show you what one of these looks like. This is what I built after my bootcamp. And with that, this series is coming to a close. Yeah? Right. I'll show you this. So this is my token shop, which is big for some reason.
It's cut off a little bit on the left side.
I know. What the heck? I think my monitor, like, it's like my monitors. Oh, what? What happened there? It's been a while. So I did this presentation at Edge actually. Which one do I want? No. A couple weeks ago, and somebody had looked up like my how does this work? Who knows? Somebody had looked up my my website and went to this and was like, "Hey, I tried to do your thing, and it didn't work." And I was like, "Of course it works." And so I had this like back and forth with this guy, and it ended up it didn't work because it's a really nice little. It's a little kind of logical kerfuffle that happens with this. I'm not going to tell you what it is, but if you want to talk about it, we certainly can. But basically, when I initially did this, I did this with oracles. So you can basically buy Toby tokens with Ethereum. Now I wrote it because now stable tokens are so synonymous. It's a swap contract, so it just swaps out whatever you want. I've checked it, it does work, but you would basically like approve an ERC20 token. I've already done that. And then you would trade that. And the whole thing here was that, so basically I'm gonna trade one USDC for one Toby token, right? And I'm able to spend like a lot of them. That's not how many I have, that's just what the approval amount was. And there's a little bit of contract introspection, but this doesn't do a lot. It just basically is one component of a social project that I made where you buy these online and then you come to me in person. I'll pay you back in cash and you can burn the Toby tokens, right? And so if I do this, I'm basically going to spend 13 cents on Arbitrum to buy a Toby token for 1 USDC, right? And then that happens, and then I think I should, it's pretty fast, I might have already missed it. If I look at my assets, I've got, I had 5, now I have 6. So, and then I paid 1 USDC for that. So, if you wanted to actually look at that, I'm not lying, but it does work. And this is what I built. It was, so this is on Arbitrum mainnet. You can talk about L2s if you want. But I thought the Oracle was a little bit more interesting, where it actually would do the dollar conversion of the price of Ethereum. But I used an Oracle service that changed their API and then bricked the contract. So that's also something to think about. Is if you're using a infrastructure provider that changes their API or changes how their technology works, and it's a smart contract that you can't change, they could be the ones that make your contract not work anymore. So that's a good lesson there. It was not Chainlink, but now you can do on-chain price calls and things like that. So it's very simple, but before you actually had to scrape a price out of a URL and then send it back. So it's kind of fancy, but also doesn't work anymore because they changed the way that they do that. All right, and I think, Cloud, you want to come up here to do that? Or do you want to go in the workshop? Do you want to take a break? What are we doing? I'm done.
Yeah, I mean, shoot.
Oh man, don't.
Let's give it up for Toby. That was amazing. I guess, do you guys prefer doing it in the workshop or up here for Cloud's workshop? We can do governance here, right? We can vote on what we think.
Ooh, purple shirts.
Purple shirts. So who wants to do it up here? Workshop? Oh, we'll take a break regardless, but workshop? All right, we'll do workshop. Last thing I want to say is thank you guys so much for this. This has been a trip. We did 7 weeks, trial by fire. Had no idea what was going to happen, but I think it was really successful, and we're excited to continue this boot camp and do another cohort and another one. You guys are the genesis block of this boot camp, so congratulations. And shout out to all the mentors, every single one, from Toby to James to Cloud to Adrian, right? So let's give everyone a round of applause. Great job, everyone. Thank you so much for coming.
And to you, we are very proud of you.
And to you guys, of course. Pizza's coming soon, in like an hour or so. And we've got some hard seltzers.